Good afternoon, sir. Rajashekar, sir. I'm audible.
Yes, sir, I'm audible.
ರಾಜಶೇಖರ್ ಸರ್ ಕೇಳಿಸ್ತಾ ಇದೆಯಾ ಮಾತಾಡ್ತಿರೋದು?
Yes, sir, ಕೇಳಿಸ್ತಾ ಇದೆ ಸರ್.
ಸರ್ ನಿಮ್ಮ ಸ್ಲೈಡ್ಸ್ ಒಂದ್ಸತಿ ಟ್ರಯಲ್ಸ್.
ಇದು sir, this is somebody else slide, I think.
ಶಶಿಧರ್ ಸರ್ ಅಲ್ಲ.
I'll share my screen, sir. One second.
ಓಕೆ ಸರ್, ಓಕೆ. ಶೇರ್ ಸ್ಲೈಡ್ಸ್ ಚೇಂಜ್ ಮಾಡಿ ಸರ್, ನೋಡೋಣ. ಚೇಂಜ್ ಆಗ್ತಾ ಇದೆ ಸರ್, ಚೇಂಜ್ ಆಗ್ತಾ ಇದೆ. ಸ್ಟಾರ್ಟ್ ಅಟ್ ಶಾರ್ಪ್ 3 o'clock, ಸರ್.
Sir, am I audible, sir?
Yes, sir. Audible.
And my slides are moving, sir. Is it fine?
No, sir, just now you changed the settings, slides. It's not,
Because I have
yeah,
already gone for full mode.
okay. Yeah, now it is,
Is it visible now, sir?
yeah, now it is visible, sir.
Okay, sir. So, do you want me to be on video?
Sir, if possible, okay. If both audio videos, that's better, sir, I think.
I'll go for full slide, sir. Then start with my session based on your permissions.
Okay, hey, sir, sure, sir. At 3 o'clock, shop will start, sir.
I
Still,
can start
participants,
at 3 o'clock.
yeah, still participants are getting into the
Sure,
Zoom.
sir.
Still time is there, sir.
Sure, sir. I'll be
Okay,
waiting.
sir. Okay, sir.
Register number 24, Chintan. Absent.
So good afternoon, everyone. Hope I'm audible to everyone. Hello.
Yes, sir, you're audible.
Okay, dear participants, we'll start the session. Dr. Rajashekar Kunabeva, the HOD, Department of ISE, from SKSVMACET, Lakshmishwara. So over to the Jayadevappa, sir.
Good afternoon, everyone. It's our honor to welcome Dr. Rajashekar Kunabeva, a distinguished academician, researcher, and administrator in information science and engineering. Dr. Kunabeva serves as a professor and head of the department at SKSVMACET Lakshmishwar. With over 23.5 years of academic experience and 3.3 years in industry, Dr. Kunabeva has made significant contributions to teaching, research, and innovations. His research expertise includes digital signal processing, computer networks, and AI-driven biomedical applications. Dr. Kunabeva has held various leadership positions, organized conferences, and published numerous research papers. He is recognized as a recognized research supervisor and has received awards for his contributions. We are privileged to have Dr. Kunabeva with us today. His vast knowledge and experience with undoubtedly provide valuable insights to us all. Please join us in extending a warm welcome to Dr. Rajashekar Kunabeva. The session is over to you, sir.
Thank you, Sandeep. I think it's high time that I will just share my limited knowledge to you. There are many learned professors here in this group who might have much more knowledge than me, but still I would like to give some basic insights into the topic on which I have worked a bit. Hope my slides are visible and moving, sir. So welcome everybody. Good afternoon. I think I'm audible, sir.
Yes, sir. Audible, sir.
So my topic of research is based on cardiac arrhythmia detection. I've been working since my PhD here, and I have touched upon advances in CS-based deep learning techniques for cardiac arrhythmia detection, which is the extension of my research work. So we'll come to that CS-based deep learning technique at a later point of time. CS stands for compressive sensing technique, a novel technique here. And as an introduction, we can see about the cardiovascular diseases is the number one killer across the entire world. Particularly for India, we are having 26% of the deaths are due to non-detection or late detection of CVD here. And about the topic here, I'm focused on arrhythmia. So basically, our heart beats with a permitted rhythm of 60 beats per minute to 100 beats per minute to call it as a normal heartbeat. Any deviation or disturbance from this particular rhythm or number of beats is called as an arrhythmia. Basically, there are 27 different types of arrhythmia which are there, and they are very hard to detect. Some of them are life-threatening, and we use ECG signal as a fundamental tool for analysis of the functioning of the heart. And ECG signal has been used in last 70 years, but still there is a lot of hidden information which cannot be captured, which cannot be analyzed by the devices of the technology which is present at this point of time. So therefore, ECG represents the electrical heart, and on the right hand side, we are able to see there is a diagram which speaks about the normal ECG signal consisting of PQRST waveform. So analysis of this PQRST waveform will be giving us about the insights of what is the disorder of the heart at this point of time. There are number of tools which have been used based on time series analysis, based on frequency analysis, based on wavelet analysis also. Many people have done the work. Today, with the disadvantages of the previous techniques, deep learning has evolved as one of the most powerful AI tool for analysis and detection of the arrhythmias, which are occurring in many of the people. It goes undetected. So now the question is why we require artificial intelligence. Just because industry is floating AI techniques and encouraging deep learning and convolutional network and machine learning techniques all across, we need not use those AI techniques here. There are certain advantages what AI offers when compared to the trivial techniques which has been present in the literature. So AI offers a quick and accurate interpretation of images or signals in general here. An image is basically a 2D signal. So therefore, we can rely on artificial intelligence for a shorter time analysis. Within short time, we will be getting a quicker and more accurate analysis as compared to the wavelet-bound techniques also. And it is having the potential to make healthcare more efficient, and you can bring down the cost. So that is what is ultimately required. As an end user, I don't want to spend more money going to the hospitals and spending lakhs of rupees uh, for a particular event here. So if it is detected early at the point of care or very near to me, where my watch or any other wearable device is able to detect and tell me in the initial stages, then all those different problems like cardiac failure, cardiac attack, all those things can be avoided here. So in this way, it's going to help cut down the costs. And what is the primary objective for utilizing artificial intelligence or AI in analysis of ECG or interpretation? It's very simple here. The objective is to develop comprehensive human-like interpretation skills. See, till this point of time, no matter what we claim that wearable devices are in market, we purchase those things, and we wear those things for detection of the heart rate variability. But still, those devices are not reach the accuracy where a doctor is replaceable. A doctor is a human who is having a very high skills in interpretation or analysis of an ECG signal. So therefore, AI has got the potential to work parallel with the human-like interpretation skills. It's possible. So basically, AI consists of machine learning and other algorithms or the techniques here, in which my topic is completely focused on deep learning, as deep learning has proved to be one of the most powerful techniques which is able to simultaneously match all the performance metrics of a particular algorithm here for detection of selected arrhythmias. So this is a block diagram where the trivial machine learning technique, how it is going to function for detection of an cardiac arrhythmia. ECG signal is read, and then we have to go for selection of the features, because feature set will determine the subsequent classification accuracy and the decision making stages here. So feature selection or feature engineering should happen in a proper way. There are certain algorithms where machine learning techniques can be applied for generation of features or generation of feature set. This is one point where we can definitely do some research work here. After feature set is developed, then we can use any one of these supervised or unsupervised learning techniques, which both of the categories belong to machine
I
learning.
have changed the values just to keep it very simple.
So therefore, supervised or unsupervised learning, then we can go for classification. In classification, there are multiple techniques here. Symbolically, I have represented as regression techniques or clustering techniques can be used. After classification, then you're having the decision making about what type of arrhythmia this is, whether it is a bradycardia, whether it is a tachycardia, whether it is a premature ventricular contraction. So many other things are there which are associated here. So therefore, this is about the basic machine learning, end-to-end block diagram here. We can see further that how AI technique is going to, replace this ML approach. So from the human being, we capture the ECG signal. That ECG signal will be having, this is only one cycle, one complete cycle of the ECG, where features like PQRST of the ECG signal is noted. In this is a normal ECG signal. Suppose if there is a rhythmic disturbance or there is an arrhythmia, then these normal features will not be present. Either magnitude of the signal will be changing in certain portions, or it will be having a variation in the time series, horizontal axis here. So based on this, the AI system is going to read and perform all the data cleaning or pre-processing stages. It is also going to take care of selection of features, unlike the machine learning. In machine learning, in the previous diagram, we have seen feature engineering has to be separately done. ML is not taking the responsibility for this, or ML algorithms are not taking the responsibility. But in AI, you just feed the data. Based on the property of the data, it is going for preparation of the data cleaning, then feature engineering automatically it's going to do. Then it's going to also go for classification, and ultimately we want a decision what type of arrhythmia it is. So that is going to be handled end to end by AI algorithm, provided we use the raw data like an ECG signal. So AI offers three important performance improvement here. Improved workflow is very good here, and diagnosis accuracy will be much higher than that of the other trivial techniques, inclusive of the generic ML. Improved prognosis also is going to be one of the observed features through the literature review. This diagram I have taken from 2025 paper published in January. So therefore, this is the basic fundamental difference here. And because AI models, many AI models are there, some of the observable and successful AI models which were observed through the literature by seeing the performance metrics are the following here. In ML or machine learning algorithms, usually they deploy support vector machine, random forest, decision tree, and k nearest neighbor, and Nave's Bayesian algorithm, which is based on the probability theory. These are successfully detecting either the accuracy or specificity, sensitivity, F1 score, recall, and these are all the 5 parameters which will be frequently used for rating the performance of the algorithm in detection, successful detection of arrhythmia. Likewise, in DL or deep learning algorithms also, there are so many variants. From the fundamental artificial neural network, ANN, we are having convolutional neural network, then recurrent neural network, then GRU technique, then long short-term memory, and bidirectional LSTM, and latest one is transfer learning. We'll be looking into the selected portions of this. Below this, I have selected one diagram. I think it is moving towards the left. This CNN technique is most associated with the deep learning one. So therefore, convolutional neural network, you can see the generic diagram, how the, if we feed an ECG signal to this, what are the inherent components of the convolutional neural network or CNN network here. It is easily able to classify what type of animal it is. Likewise, even I can use the same CNN for identification of arrhythmia. So here, an animal picture is put here. This is in 2D image, which is acting like a kernel. From this, you are having the pooling stage or pooling phase, where convolution and ReLU is going to be computed. Like this, you are having multiple phases where pooling phases are having stage 1, 2, 3, 4. So in these pooling stages, we are going to extract the feature maps. A mapping of entire features is going to be done. And by the time it reaches the flattened layer, vertical layer here, we would have performed the feature engineering or feature extraction is completely done. At this stage, we are having access to the array of an array consisting of all the features of that particular animal or in equivalently ECG signal here. Thereon, afterwards, we want to go for classification. In classification stage, we can apply the deep learning algorithm. So a deep learning algorithm is usually based on its specification. How do you identify the DLL algorithm here? So DL algorithm is having many number of hidden layers when compared to the trivial artificial neural networks. So the number of hidden layers defines the depth of the particular layers or the algorithms for which can be used for analysis of a particular signal or image. So this forms the fully connected layer. The very first layer, which is flattened layer, connected is all the features are going to be mapped and passed through the neurons. That is the input layer. Then intermediate layers are hidden layers, and the last layer is the output of the decision layer here, where based on the probability distribution, it is classified into horse, zebra, or dog, etc. Likewise, horse, dog, and zebra, what is shown in the diagram, can be mapped to arrhythmia 1, arrhythmia 2, arrhythmia 3, etc., etc. Right? So therefore, because I told that there are 27 types of arrhythmia, we don't know which ECG signal is having what type of arrhythmia. So like this, we can use CNN network for classification of the and identification of a particular type of arrhythmia. Yeah. So I have taken this diagram for showing that 2D images of the can also be applied for the DL algorithm. Not only a single dimensional signal like ECG, both can be applied. Now, what are the problems with the previous methods and why AI has become more prevalent with respect to the biomedical domain now? Previous methods were designed and developed and coding was done based on pattern recognition, or we made the filter adaptive. We were dependent on statistical analysis like mean deviation, etc. Then correlation or similarity based methods were applied, and logical or thresholding rules. Histogram approach was also applied for two-dimensional ECG image, that is an image of the particular ECG signal, and wavelet entropy based method, discrete wavelet transform based method. Many previous methods were applied. There were certain limitations which are observed in all these previous methods. I have mentioned only few. There are many other also in the literature. So limitations for all these methods are based on a particular decision logic. And the most important one is the second limitation, not fully automatic. End-to-end automation is not possible by using previous methods. Again, human intervention was required, and programmer has to go for analysis and intervene at every stage. Either feature engineering, again after this classification, this intervention or analysis and recoding was required here. So not fully automatic here. That is what is desired in nowadays. We want a fully automatic system. So that is why AI is more preferred here. And we always require the intervention of the external, that is person here, when the subject is changed. In this case, biomedical, for biomedical case, subject means it is a person. When a person signal is changed, when a person changes, his ECG signal is definitely going to change. So person 1, patient 1, patient 2, patient 3, like this, we require intervention in the previous methods. So actually the algorithm which we are going to place for detection of cardiac arrhythmia should perform independent of the person or a patient who is going to be tested using that algorithm. So this is the limitation of the previous techniques here. And the techniques which are based on time frequency representation have issues with the computational complexity. See, we are trying to access the time and frequency at the same point of time, extract the features, and this computational complexity will increase. One example of TF representation of the data is discrete wavelet transforms, DWT transforms, which we come across in the many of the arrhythmia detection techniques in the literature. So how to overcome this? Now all the limitations we want to convert. For example, second one, it's not be based on decision logic only. It should be made fully automatic. It should perform, the algorithm should perform independent of the person or the patient who is going to be tested. So we want a device which will be able to perform and test and detect accurately irrespective of which patient is going to be connected to that particular device. So all those things, and we want a lesser complexity, computational complexity. So therefore, I'm going to choose such a representation. So therefore, which are those, all these features are available in AI methods, particularly deep learning method here. So therefore, I'm directly going for moving to the deep learning technique. So which are the two fundamental, powerful things which can be observed for a deep learning technique here? High level feature extraction and classification can be performed automatically without human intervention, and in contrast to the ML models, because machine learning models were dependent on, in this diagram, I'll go back to this diagram here. You can see machine learning model is totally able to perform only after handcrafted features have been extracted here. Handcrafted means a programmer has to extract the features after writing the code and give that feature set to the any of the machine learning techniques. Then only it is able to classify properly. If a programmer performs feature engineering and an error is crept in, then automatically machine learning technique will not be able to perform better or detect very accurately. But in artificial intelligence, we are having end-to-end solution. You feed the data and everything is automated until final decision is going to be announced or taken back. So therefore, taking this here, vast data volumes and optimized data processing strategies are possible if the data volume is increased, the data set is increased. The meaning is, if the patient set is suppose 50 patients data I have given, then machine learning can very accurately perform and it can be able to detect the arrhythmia properly. Suppose if I give 600 patients data or 1000 people's data here, then machine learning techniques will not be able to handle that volume of the data. For that, we are having the deep learning techniques, and different optimization techniques are also available using the DL, which are more accurate than the ML. These are the two important places where DL and particularly machine learning techniques differentiate with respect to each other. Now, having said this, let me focus on what about the deep learning here. So deep learning has been found to be well recognized or widespread recognized for its effectiveness in classifying particularly cardiac disorders. In 2025 paper, more than 100 and something odd papers have been listed for literature survey for different stages for cardiac disorders. In that paper, very clearly, DL techniques are dominating in the literature survey. And we can apply deep learning techniques for both supervised and unsupervised methods, unlike the other techniques here. And we have the facility of increasing or having numerous hidden layers between the input and output layers. That means the depth of analysis can be taken by occupying more hidden layers to reach the accuracy which is required here. That facility we are having, that feature is available in the deep learning algorithms. And any DL model, deep learning model, will facilitate specific choice of layers. Depending on the nature of the problem we have taken up or the problem it should be addressed, then we are able to specify the choice of how many layers you want to go for. Whether you want to go for 3 layer, 4 layer, or 10 layer, or 15 layer, etc. That can be decided using DL. And how deep learning has become so much powerful and widespread, and it is able to succeed in detection of cardiac disorders in general. What I have observed, it can be present for other images also. So one few reasons are, it's able to take the CPU power, lesser CPU power, and extensive data sets or larger data sets or volumes can be handled easily. Inside the deep learning technique, we are having a very important component called as convolutional neural networks. Trivially, ANN were there. Instead of that, convolutional neural networks or CNNs are being deployed in DL. So therefore, this is giving rise to the better accuracy of detection. Why CNN now? There is one question. So it is observed that CNNs are having the capability to work directly with the raw images. See, images will be, or signals will be consisting of noise which has crept in, or disturbance which is taken when we capture the image, and all those things is there. So therefore, we need not clean the data and clean the image and give that image here. Directly we feed the raw image or the raw signal to this. CNN is capable of taking that raw image with all the noise, able to remove that noises, clean the image, and then do the end-to-end data processing. So autonomously, it is able to learn the features from the training data here. This is the important or significant advantage of the CNN, why it's preferred to be a component of DL. Now, deep learning models also demand a substantial amount of the labeled data here. The meaning of this is we cannot provide the data which is unlabeled. Annotation has to be performed. We have to give the description of that particular patient record and feed it. So this is the one important thing which a deep learning model has to be. It is minimum requirement. So we can go for cardiac arrhythmia detection and classification using one-dimensional ECG signal, time series signal, or we can go for taking images, printout of the 2D. So this is the basic block diagram for cardiac arrhythmia detection using DL approach here, where you can observe that input layer and output layer is single, and in this case it is shown as 3 layer because we have the flexibility to choose how many hidden layers is possible. We can go for extension of hidden layers as the case may demand here. Okay, in this we are seeing feature engineering, classification, both are being handled automatically from feeding the raw data to the final decision or diagnosis output. Now here, because I have spoken about ECG alone, now I have taken one example where network components or deep learning network is also CNN is a component of DL, so therefore we can treat it as a network of different neurons here. So therefore, basic DL network components, we can see that how to go for recognition of an image. So for every image, you have to extract the patterns of the local contrast here. So therefore, I'm taking the input, multiple input layers are going to be taken, converted to the respective scale, and hidden layer 1. In that, we are going to extract the features of every face or the image which is present in the input. After doing the feature engineering, this is being automatically done by a DL alone. We are not the human intervention is not there in the form of programmer, or no coding is going to be done. So this is being done by the DL only, deep learning algorithm. Next one, we recognize for the features here in the last hidden layer 2, then the output layer is available for us to go for recognition of the particular face out of the available images here. So the number of hidden layers varies from the property of the signal or the image and the quality of the data here. So that is variable. If it is able to reach early, then the layers will be less. Then this lesser the number of layers, the faster will be the computation speed and the reconstruction of image is possible, or recognition of the image is possible, or the face is possible. Now I will deviate. Having said about the DL, I will come to touch upon very quickly upon the sampling techniques here. There are n number of sampling techniques where we choose the data for compression here. So therefore, sampling rate, whatever sampling rate we fix, it determines the lifetime of a sensor node. Suppose we assume that we are trying to capture a data using camera, or we are trying to capture the ECG signal using a sensor node and transmit to the remote location. In that place, how do you capture the data? So trivially, capturing of data in 2D or 1D signal, everything is going to be was dependent on Shannon's-Nyquist sampling theorem. We know that the Shannon's theorem states that the sampling rate should be at least 2 times that of the highest frequency component in the input signal. In the diagram, very clearly we can see input signal is x of t, a signal or an image, both are same. Then Nyquist sampling rate, Shannon's sampling rate is going to be chosen for selecting the samples or portion of the ECG signal or the images. Then compression is performed. Afterwards, the compressed version of the signal was available here. Now, what is the problem with this Shannon's or Nyquist sampling theorem if applied here? So we can observe 2 to 3 different limitations. It doubles the quantum of the captured and eliminated data because we are multiplying 2 times that of the frequency component. The number of samples which is required, the amount of the captured and eliminated data is going to be more. Let me put some light on this. The quantum of captured data is 2 times because capturing also we increase by 2 times that of FM, that is sampling rate. And when the signal is supposed to be reconstructed and shown to the user at the receiver's end or at the medical whatever expert end here, there also we have to remove the redundant data or the repetitive data. That is also 2 times. That is why it doubles the quantum of the captured data. Then we do process all the twice of the data throughout all the stages, pre-processing, then processing, then classification, then decision making. Then afterwards we have to eliminate all those things. After compression and decompression, we have to eliminate again. So much energy is lost and it will reduce the lifetime of the sensor node. So therefore, for this case, we don't prefer the Shannon's-Nyquist criteria for sampling the data here. So therefore, there is also one more thing. For increased resolution, we require the increased rate of sampling. Very fundamentally, the energy spent for capturing any data or processing any data depends on the number of bits. This number of bits is nothing but equal to the resolution. So resolution is nothing but the number of bits used for representing one sample of the data. It is pixel or it is one sample, whatever it may be. So therefore, how to reduce this number of samples so that the energy spent by the sensor node for capturing the data will be reduced and the sensor node will be available for longer time. For this, we got an alternative in compressive sensing or sampling techniques. So compressive sampling techniques was there. What they did inside this is the sampling theorem Fs, sampling rate Fs was brought much lesser than that of the 2 times that of the FM. So therefore, in this by doing this, compressive sampling means at the time of sensing the data or capturing the data only, we select which samples to be captured, which samples to be selected here for compression and further transmission. That is simultaneous sensing and simultaneous compression is possible. That is called as compressive sensing technique here. This compressive sensing technique is a replacement of the existing Shannon's-Nyquist theorem. This compressive sampling technique was found out in 2006. That is proposed, and later many algorithms have been done here. By using this, we are able to reduce the number of bits at the source. Once we capture lesser number of the entire data using lesser number of bits, automatically you are eliminating the need for encoding the different all the data here. Need not go for sending all the data or twice that of this. So therefore, at the bottom I have given one small equation here. FCS, the sampling rate of the compressive sensing is much lesser than that of the Shannon's rate. What is the meaning of this here is, in Shannon's theorem, we require n samples if you are transmitting. Then in compressive sampling, we are having only m number of samples, which are much lesser than n. To give an example here, if n is equal to 100, then if you use compressive sensing, then the number of samples which you are capturing the entire data with the same quality will be much lesser than n. Maybe it is around 40 or 50 or 35 like this, right? So therefore, this is a simple example of compressive technique here, sampling technique here. Traditionally sampling, compressive sampling, how it is mathematically implemented here. So towards the left side of my diagram, I'm having a signal of x. So I'm having totally of 8 measurements here. So this is equal to one matrix called as phi. This is a sensing matrix. What is the role of this particular matrix, a binary matrix, which is indicated as phi underscore TRD? So this is used for selecting only particular samples from the raw data. Where is the raw data inside this diagram? So the last whatever column you are seeing, this is the raw data. From this raw data, we need not select all the samples. We will select only those samples which are permitted by this particular sensing matrix. How it will happen? Wherever 1 is there, that will get selected. Wherever zeros are there, all those samples will be multiplied, or values will be multiplied, and they will not be sampled at all. So this is the basic funda of the compressive sensing technique here. Therefore, when we go for multiplying this phi TRD matrix or sensing matrix with the raw data on the right hand side, we will get a compressed version on the left hand side, which is showing only 8 values. So therefore, here the number of measurements are large, which is capital N, and the lesser number of measurements is possible here. So this is about the compressive sensing here. I am showing the same diagram here. Now we need not focus on each and every aspect. Let us focus on only simple thing. The compressed vector is denoted as y. This we can get by sampling the raw information or raw ECG signal or image which is kept in X vector. And how do you select only few samples here? That will be done by the matrix called as that is sensing matrix, which is denoted as phi in this diagram. So therefore, whatever binary matrix is visible on the right hand side of this slide, binary matrix is there. This is nothing but equal to phi only, right? So here I have given the symbol in the equation, but on the MATLAB I have used the phi underscore TRD. So the function will be whatever matrix you are designing here, that will be responsible for selecting the few samples out of the available n number of samples. Thereby compressed vector will be available here, right? So this is very important for us in the compressive sensing. Now what is the challenge inside this? How can I accommodate deep learning here? Now we are having challenging where and all design is possible inside the compressive sensing here. So this is the end-to-end this one here. We acquire the signal or capture the signal. Here in the blue color box you are able to see acquire signal. What will happen? A raw signal X is given. This is the raw signal, and it is being only few samples out of this. Total samples are 1 to n. We are selecting only m number of samples, where m is less than n. So therefore, the dimension of the signal is reduced from n to m. So that the vector called as y is created. So therefore, that will complete the acquisition here. So therefore, I am having one option to design compressive sensing here by selection of the compressive sensing matrix or sampling matrix. I can include deep learning technique. So DL technique, appropriate DL, lightweight DL technique is responsible for design and implementation of the sampling or sensing matrix denoted by phi in this diagram here. So likewise, reconstruction also, it is possible by selecting appropriate phi here. So all the places, and towards the right hand side, reconstruction is there. There also we are coming across one matrix denoted by psi, mathematical symbol psi, right? So therefore, in this case also, which is the psi, what should be the content of the matrix of psi, that can also be decided by the appropriate deep learning matrix. So at both the acquisition side as well as the reconstruction side, we are having the option to design two different matrices. Those matrices can be selected by deep learning models, and this is basically a dimension reduction method. So At the bottom left hand side, I've given one statement: designing sensing matrix for random choice of samples from the sensor nodes is possible here. Here we can introduce the deep learning here. So therefore, I'm having three components. We can go for designing the dictionary side, selection of designing of the sensing matrix, or when you multiply both of these things, we'll be getting the third step, that is reconstruction matrix theta. So in all these three places, we are having the option to design or apply the DL here, deep learning techniques. Any of the deep learning techniques or algorithms can be applied. Now, having done with this, so I don't want to, already I have told about this. Now I'll just open one small program which is I have written here and explain the main important things here. So therefore, let me sorry, I think it's not able to open. Let me go back to this. Just allow me to reach that particular folder here. I maintained it a pen drive. So here we can definitely see, I'll show you the small MATLAB program which has been written here. This is the MATLAB program. I think it is not linked. So here we can see how to apply the MATLAB program for arrhythmia detection along with the compressive sensing technique here. So I've written a small code, whatever fundamental code is there. And in the first step, what we do is we load and pre-process the ECG data here. So this is going to be automatically done here. But for explanation purpose, I've extracted this particular code. So first load the whatever signal we want. So I have written load DIH ECG dot mat here. This is the appropriate input ECG file. You can replace with whatever data you are going to feed, because a lot of other signals are there. Then you can copy this data and into the matrix called as ECG signals, and you will be able to see the you can allocate whether it is the labeled data or unlabeled data by assigning 0 is equal to 1, and if it is a arrhythmia, you can assign it is equal to 1 here. So this is this. Next, you should perform the normalization of the ECG signal. So in this, we have created one matrix which is loaded raw matrix. You should go for normalization of this by calling a normalization function. This is going to be done by the MATLAB automatically, but we need to understand how it's working inside this, right? Next, we are having so much of larger data set. I have taken MIT BH data set consisting of 48 records. I have to divide these 48 records into training and testing data set. So for this, I have generated one random number for reproducibility. Then we have partitioned this, okay, into two different portions, and we have stored it or labeled it as training data label and as well as the testing data label also. Very clearly, you are able to see this, right? So after this step, you have to apply the compressive sensing. So for applying compressive sensing, the fundamental, at least the data or the metric you should give as an input is what should be the compression ratio. Means what should be the 50% of compression you want to perform, or you want to go for 60, 70%, 80% compression of ECG signal you want to perform. This will decide the different factors of the compressive sensing methods here in relevant to that particular equation. Okay? Whatever y is equal to 5x as given. So next one, you have to go for designing the measurement rat, that is the matrix, which is going to be generated by feeding the random number function here, rand_r function, then round it off to the dimension of size of train data comma 2, whatever is there, then multiplied by 50%. I have taken 0.5, so 50% will be there. Then determine what is the size of that particular data which is available. Next, it is time to perform compression of these signals. The matrix which we generated, measurement matrix phi or sensing matrix, or the matrix responsible for selection of samples, that is called as the measurement matrix. We apply it on both the testing data as well as the training data, and the compressed version of both the trained data compressed version, trained data of compressed version is available, and the testing data also is available. The same sensing matrix can be applied for both the tested data as well as the training data. Next one, it is time after compression has been performed. Next, you have to build the train the deep learning model, DL model here. So in this, I have utilized CNN architecture, convolutional neural network architecture here for the, and I have declared right hand side. I have made it as bold for how many input layers I have taken, and all those things. So one input layer, then convolutional layer, then I perform the activation. Neural networks has to be given some activation function. So I have chosen the appropriate one, which is suitable for my work here after trial and error. Next one, I'm using the pooling layer. So many layers are there within the CNN architecture. If you observe the diagram of even from any of the literature here. So input layer, convolution, then activation, then pooling layer and fully connected of FCN layer, last one activation layer and output layer. So in the output layer, after passing through all these things, it is going to classify into two things here, whether the arrhythmia is the signal, ECG signal is a normal ECG, or it is classified as one of the, whether it is an arrhythmic signal here, it consists of arrhythmia or not. So like this you can do. So next one, you are having the training options. For this also you are having options. Our training options has to be declared here, maximum, so epoch size, all those things has to be declared, initial learning rate, all those things has to be set here. Then train the model. After the training, the model is going to be over. The data is stored in net matrix here, matrix called as net. That is one of the variables. Then you have to evaluate this. How will you judge that a particular DL model which has been trained by setting the above parameters is able to detect the properly 100 out of 100 times, or accuracies? If you are giving 80 signals, then it has to be accurately identifying all the 80, right? So what is the percentage of accuracy that you have to find out by evaluating this model? So that is going to be done by internally. It's going to classify and feed the raw data and tested compress the test data, which is compressed version, which we created about here. So afterwards we are going to extract or compute the accuracy value here, right? What was the accuracy level of each and every ECG patient record you are going to feed into this particular DL model, right? For everything it's going to be calculated. I had told MITBH is 48 records, so all 48 records it will be calculated, then average of 48 will be taken for claiming that this is the accuracy of the uh, arrhythmia detection for the given data set. Like this we are having, if you go to the website called as PhysioNet, you are having PCB data set is available, PTB data set is available, which is 16 channel signal here. So many other data sets are available here, right? So that depends. I have tested only for MITBIH. You can definitely test it for other things also. So after calculation of accuracy, we are having something called as confusion matrix. We are using, you are already aware of what is the confusion matrix, which speaks about the true positive, true negative, false positive, and false negative here, right? So that matrix is going to be, computed here, and it is going to be drawn. So we plot the confusion matrix for visualization, and it will show us about the normal and normal ECG signals out of 48 records and arrhythmia here. So all those things, the numbers will be present here. Next, you can visualize this. You want to draw the graph and plot the original and compressed ECG signal, right? So you can plot and compare what was the original ECG signal looking like and how the compressed ECG signal look like. You can plot it in one above the another one by using the subplot command here, right? So this is original ECG signal, and then the compressed ECG signal extracted from the data. That compressed version of the signal is present in a vector called as train data compressed, which we created, and we are extracting the very first row here and all the columns. So classification results also can be plotted to go for visualization, and you can announce for 0 or 1 and all those things. So this is actually basic and very, very basic fundamental MATLAB program, which will be able to write and test and do some experimentation. Why this is required means, if you are only feeding the data to all the tools, then we'll never be able to understand what is happening inside this particular model. So we need to get hold of the entire DL, that is DL model, whatever model we are using here. Likewise,
ಹೌದಾ
and coming to this conclusion, this is about the fundamental work
ಅವರು ಅಷ್ಟೊತ್ತಿಗೆ
which you
ತಾನೇ
can
ಹೇಳಿದ್ರು.
definitely perform.
ಒಂದ್ಸತಿ ನೀವು ಇದ್ರ ಹತ್ರ ಹೋಗಿ
So having said about this, we'll shed some light from the literature. What are the challenges we are going to face in case I want to pursue, work on this particular cardiac arrhythmia? So especially classification stages here. It all depends on the quality of the data and the variability. That is one important thing we have to observe. If we don't clean or denoise the signal, ECG signal, then definitely the conclusion or the decision will become wrong. So always the first stage, pre-processing stage, the model has to include the facility for cleaning the data at the utmost one. No single noise should be present to or fed to the subsequent stages. Okay, otherwise it will be treated as a part of the signal and it will go for misleading the classifier. Next one, you are having class imbalance. What does this mean actually? If you take any data set here, randomly ECG signals are fed in real time. Some of the out of 27 types of arrhythmia, maybe around 10 or 12 arrhythmias are very frequently occurring in the practical aspects in the field here in real life. The other types are rarely occurring. One among the 1,000 people or 10,000 people that particular arrhythmia is occurring. So now the model, DL model, what is used for testing or identifying the type of arrhythmia, this will not be able to give a fair chance or fair decision about the rare type of arrhythmia which is fed into the signal. So therefore, there is always a balance should be struck between the frequent types of arrhythmia and rare types of arrhythmia. What is the meaning of this? If I give 5 types of frequently occurring, arrhythmias here, I have to also feed the 5 types of rare types of arrhythmia and test whether it is able to pass the it is able to clearly identify rare types and frequently occurring arrhythmias or not, right? So for every model or the DL algorithm we develop, we have to test for both the types equally by taking equal number of patients. Then only the result will be correct here. Next one is the important, very important aspect is inter-subject variability. Now it is acting like a hurdle for creating universal applicable AI. Now suppose I am having an idea that I want to create one algorithm which is going to identify any type of arrhythmia, irrespective of the patient who is going to be whose patient record is fed to this particular algorithm, or irrespective of the country or anywhere across the globe here. This is very difficult. Why? Because as the patient changes, his ECG record also changes. From country to country or place to person, place to place, the subject or the person will be changing here. So therefore, there will be definitely small variations will be observed between the ECG record for a particular arrhythmia only. ECG record of patient 1 will be definitely different from patient 2 and patient 3. This is called as inter-subject variability. So this is going to definitely create a problem in designing a very stable and mature AI model, which is capable of identifying arrhythmia when the patient changes in the particular hospital. Right? It will take a lot of time for creating a universal applicable AI here. Then temporal dynamics, time series dynamics will be always variable across the horizontal axis. That is also changing. So you have to keep all the dynamics or changes in the time series axis or horizontal axis and design the AI algorithm. Right? You may have to go for hybrid models also. And not all the ECG data sets are annotated or they are not marked the features on the signals which are present on the internet for analysis or research purpose here. So annotation we have to manually do it and then we have to test it. Right? So this is one thing. Annotation is nothing but marking of the features like P, Q, R, S, T where it is present. Okay, what is the time duration between the features on the horizontal axis like PR interval, RR interval, okay, ST interval, etc. for a ECG signal. So this annotation or marking has not been done for all the data sets. It poses a major challenge. And next, we are having explainability AI and trust with clinical experts. See, it's very, very difficult that, whatever AI model as a technologist or a technocrat I will design, and that will be accepted or trusted by the clinical experts. There is a lot of gap there. So therefore, both have to come together. And doctor and engineer, they have to come together and start working on a common, standards here. Then only it is possible. So we cannot replace a clinical expert by the whatever AI techniques are applied. And this gives rise to the next point. Clinical validation and adoption has to be done. So whatever we may claim AI technique is mature, it is able to identify all the arrhythmias, but this has to be cross-certified by the clinical expert or a cardiologist at present days. So this, if this has to vanish and you tell that automatically AI is or a AI device or AI enabled device is capable of doing this, then you have to reach the accuracy which a human intervention or a doctor is able to do at present day. It will take some time for this. And we have to observe the real-time processing requirement. See, doing an designing an AI, applying on a laptop, and making some paper and testing for 48 records and 116 records from different database is a different aspect. And putting the AI enabled device or a wearable device and tracking the arrhythmia types in the real time, okay, that is totally different aspects, because real time processing demands that faster or early detection has to be happen without any fault, and it should be more reliable. Designing such gadgets is a very difficult task. Designing such compatible AI techniques and putting it in an embedded device is a very, very difficult task as of now, right? So therefore, and if you are choosing AI cardiac arrhythmia classification, if you are doing here, any biomedical application we develop directly, we cannot apply it to the field of human being, because it is a techno legal issue here. Whatever technology we developed, it has to be passed through the legal, take the legal permission, then only you can apply for this. This is done to avoid the hazards. If wrong decision or wrong outcome comes out of that particular device or algorithm or a printout, based on that only doctor will prescribe some medicine and something will happen to that particular patient. That is why directly we are not supposed to apply this AI technique anywhere in the field without the permission of the government agency here. Then integration with clinical flow, workflow here. Right now, clinics will perform in a different fashion than that of the AI techniques what we design in a laboratory or in a laptop or some other device here. So integration is much different. These are so many challenges are there. I request people who want to pursue research here, you can take up any one of these aspects and then dig into the literature in IEEE or Science Direct papers. You will definitely get some good quality literature and identify the research gap, and then you can take it forward, right? These are some of the research challenges which I came across in the literature. There may be a few more when you go to practical fields. So what is the future direction of CVD or cardiovascular disease diagnosis using AI? The companies will be focusing on applications of AI in wearable devices, because we people will be traveling and will be doing so many other routine things. Everybody is working, so we want a device which is wearable, lightweight, and capable of triggering or identifying the cardiac event just before it occurs and guessing what type of this one. So once your smartwatch is connected to the internet, obviously it will bring to the notice of the other people, and future catastrophe you can be avoiding by taking that person to the nearest hospital or care care. So this is the main aim of the applicability or application of AI in wearable devices. Right now, all applications are there on laptop. You have to penetrate or bring it into the wearable device. Why it is a challenge? Because wearable devices are driven on battery. If the battery is dead, the entire device is going to be dead, right? This is the major challenge here. Then early detection of heart failures. You can see many videos on the internet where within fraction of second a person is going to collapse. So detecting this heart failure or prediction, they are trying from last 60 years. Okay, it's very difficult till this point of time. Maybe some AI model will be able to do this and save a lot of people's life, right? So predictive analytics for stroke also, because there is a lot of similarity between the cardiovascular disease symptoms as the stroke here. Any one of them is going to occur here. So both of these things, prediction and analytics has to be improved. This is one area or the niche where we can thrust area where we can work here. And personalized treatment and phenotyping, all those things is there. But last three are important for us. Development of novel AI algorithms. Definitely new AI accurate with all performance metrics being well balanced. They will act like a identification of new biomarkers. What is a biomarker? A biomarker is something which is a feature of that particular signal or an image, observing which the doctor can decide what kind of treatment should be given. So therefore, that will act like a identification of new evolutionary biomarkers is possible, and diagnostic accuracy is going to be increased. So that can be done only if new AI algorithms are going to be developed, whether we use DL or any other algorithm class of algorithms which belong to AI. Then interactive and explainable clinical support. Now today what has happened is very recently GPTs, whatever GPTs are there, they are able to interpret the ECG signal using NLP technique or the natural languages. So natural languages is human spoken languages also. Whatever text we feed into the chat GPT or other GPTs which are possible here, they are able to easily analyze the ECG using natural signal. So natural language means what we describe. No, for example, we can try it out here. I have not tried. we can feed what is the interval among the RR interval, PQRS, I mean P to R interval, then QRS width here, all those things if we give it in the natural language, GPT should be able to decide and tell me what type of arrhythmia it is. So this is interactive and explainable clinical support which can be obtained. Right now GPTs are able to do by text, but tomorrow it may be able to do by image, next it may be able to do by VCG, okay, vector cardiography or 3D signal here. Last one is because only ECG signal is not capable of giving the accuracy despite application to the AI models here. Now the latest trend is we are using multimodal signal and explore the diagnostics here, explainable diagnostics. What is the meaning of this? We can use ECG signal captured as one dimension. We can take the image of the ECG signal. We can take fundus image captured from the eye, and next we can take the brain signal and respiratory signal like SpO2. So there are so many vital signals which are there, biomedical signals which are there, which are being generated in the human body. If we are able to capture the relationship between certain biomedical signals, that is called as taking more than one biomedical signal is called as a multimodal approach. So multimodal and explainable diagnostic, this can be solved by using LLM models, that is large language models, for analysis of the ECG signals here. These are few research directions which we can definitely pursue. These are the challenges, or how to go about, even though you know how to go about this is going to be questionable, and these are definitely directions where possibility of doing research is definitely available here, right? And yesterday I was learning about one another GPT engine here, KWEN. So we have to explore that also. Every day some new engine is chat GPT or GPT engine is available here. With this I think I've given some insight into this application of deep learning model as much as possible from my limited learning. I am very thankful to the organizers, and most importantly to all the participants who have beared me for the last one hour for listening to this. Thank you so much.
Thank you very much, sir. So, dear participants, if you have any queries, so definitely we'll share the slides, sir. If somebody asks the slides of this session, definitely we'll share the slides. So the madam contact details.
ಮತ್ತೊಂದ್ ಜನ ಇದಾರೆ ಸಾಕಾಗ್ಬಿಟ್ಟಿದೆ ಎಲ್ರಿಗೂ ಬಂದ್ ನೋಡಿ ಸರ್ ಥ್ಯಾಂಕ್ ಯು ಸರ್ ಅಷ್ಟೇ ಥ್ಯಾಂಕ್ ಯು ಸರ್ ಅಷ್ಟೇ ಬಂದಿದೆ
So we'll share the feedback link in a few seconds. Thank you, Rajashekar sir. It was a nice presentation, and I hope many of the research scholars helped with your presentations. And many of the faculties are asking the slides. So if you share with us so that we can share with the group within the group, sir.
Rajashekar sir has given the email ID dr.rkece2022@gmail.com. Thank you very much. And tomorrow morning at 10 a.m. I have a session with Dr. Vishwanath PS, scientist, Philips India, Bangalore. And tomorrow we'll share the link by 9:30 a.m. and the session will start at 10 a.m. exactly. Thank you. Thank you, sir. Sir.